Hi everyone. In this video we're going to examine Bohr's model of the atom. Bohr came up with this model to explain line spectra, but it took him 30 years. It wasn't until 1913 that Bohr published this model of the atom. By this point, nuclear theory was pretty well established, so we had this central core known as the nucleus. Bohr's model in particular pertained to how those electrons occupied that electron cloud. And so he proposed that electrons orbited the nucleus in orbits similar to the way that planets orbit the sun. And there are two basic tenets to Bohr's model. The first pertains to the radius, or distance that the electron is from the nucleus. He said that the electron could only exist at certain specific distances from a nucleus. And this is different from a planetary model, where theoretically a planet could be any distance away from that central sun. In the atom, we have our nucleus, and we have discrete distances that the electron can be, and it can't be anywhere else but those distances. Just like our staircase example that we saw before. We can be on any one step, but we can never be in between stairs. Now, Bohr gave each orbit a number, and it's an integer value between 1 to infinity. And we will know this as principal quantum number n. So each orbital was given a number where 1 was the closest to the nucleus, followed by 2, etc., etc. He was also able to represent this mathematically. He said that the radius of an orbit was equal to the principal quantum number squared divided by the nuclear charge multiplied by a scaling factor A naught, or A sub 0. And for the hydrogen atom, if we're talking about the first orbit, we'd have 1 squared over 1 times A naught. And A naught is a constant value. It's what we know as the Bohr radius. And for hydrogen, it would be simply equal to A naught, which is 0.529 angstroms. And each subsequent orbital would get farther and farther from the nucleus as n increased. And you'll also probably be able to find from this mathematical equation that as n is increasing, the spacing between those orbitals gets larger and larger as well. So we have uneven spacing of these orbits as we go away from the nucleus. Bohr's model also addressed the energy of an electron in each orbit. So just like those orbits can only exist at very, very specific distances from the nucleus, the energy of those orbits can only be a few limited values as well. So he was able to relate the energy of each orbit, n orbit, so the first orbit, second orbit, according to n equals 1, 2, etc., was equal to the negative of the Rydberg unit, which is different from the Rydberg constant. So the Rydberg unit, so 1 Rydberg, is equal to hc times the Rydberg constant. So if we plug in our numbers here, we can actually solve for this value. So it's going to just be another constant that we can use. 6.626 times 10 to the negative 34th joules seconds is the number for Planck's constant times the speed of light, 3.0 times 10 to the 8th meters per second. And then the Rydberg constant is 1.097 times 10 to the 7th reciprocal meters. So my units will cancel with the exception of joules, and I'll get 2.18 times 10 to the minus 18th joules. So that's a number that you might see pop up here and there. That is the Rydberg unit. And so essentially, back to our energy equation, energy of an orbit is equal to negative the Rydberg unit times z squared over n squared. And that n is principal quantum number, and z is the nuclear charge. So for the hydrogen atom, we can say for the first energy level, the energy is equal to 2.18 times 10 to the minus 18th joules. And the reason for that is because the nuclear charge for the hydrogen atom is 1. So 1 squared is 1. And then if we're talking about the first energy level, n would be 1, and 1 squared is 1. So our energy of my first orbit is negative 2.18 times 10 to the minus 18th joules. So another couple things we want to point out with respect to this equation and the result that comes from it. One is the energy. One is the sign of the number here. So what does negative tell me? Well, let's bring back Coulomb and see what he can tell me about the sign of energy. So we know that Coulomb says that the energy is proportional to Q1 times Q2, which is the charge of two particles divided by the distance. So if I have a hydrogen atom and I have one proton, that is +1, and one electron, that is -1, that are separated by some distance d, that means the energy is going to be proportional to -1 over d. And thinking about what this means with respect to Coulomb's law, that the energy will be negative when we have an attractive interaction, a favorable interaction, and indicates a release of energy, that energy is given off. And so if we think about translating that meaning back to the sign here with respect to the Bohr model, the negative sign here must imply that we're putting an electron into this orbit and energy is being released. So if we have an electron that is separated from a nucleus, an infinite distance, we would define that as zero energy. So n would be equal to infinity, 1 over infinity is 0, 0 times the Rydberg unit E of infinity would be 0. So the energy is 0. As that electron gets closer and closer, smaller and smaller n values, so now we're in n equals 1, it's the smallest that it can be. It's the lowest energy possible. And that's due to the significant attractive forces that come with being at a smaller distance. Plus and minus, attractive force, more energy is going to be released here. So we know that energy will be released when an electron was put into orbit, and opposite would be true if we were removing an electron from orbit. We'd have to put energy in. And so we're seeing an importance again of the sign of my energy. Negative, meaning released, positive, meaning absorbed or put in. Now let's take a look at our equation again and see how n influences the energy of each orbit. So we know E1 is negative 2.18 times 10 to the minus 18th joules. That's the lowest possible energy that we can have. And we call this our ground state. As n increases to n equals 2, that energy will increase. It will become less negative. We'll have a larger number. And then as it goes to 3, it increases again. But these stair steps are not going to be equal because we have n squared in the denominator. The stair steps will get closer and 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 closer together until we reach that n equals infinity. And here's a nice diagram that shows the scale of our energy levels. I want to point out here that n equals 1 to n equals 2 is the largest jump on this energy scale, even larger than 2 to infinity. And this is going to be important to keep in mind when we're solving problems and thinking about what makes sense. In summary, Bohr's model of the atom predicts that electrons will exist in orbits surrounding a central nucleus. These orbits can only exist at very specific radii from the nucleus, and the energies of these orbits can only be certain specific values as well, meaning both distance and energy are quantized. Only specific values are possible for that. Bohr was able to relate the radius and energy of each orbit to principal quantum number n. It's found that as the principal quantum number n increases, the radius of those orbits increases, and the distance between orbits gets larger and larger as n increases. With energy, as n increases, the energy will increase. It will become less negative. And those energy levels become closer and closer together as we get higher and higher n values. So thank you for tuning in and watching this video, and please do reach out if you have any questions. Thanks for watching.